Hello, everybody. So now we're going to start talking about streamwater chemistry. Now, um, the thing about water chemistry in lakes and streams, it's pretty much the same, right? Like the carbon cycle is the same, nitrogen is pretty much the same. Phosphorus, again, same impacts. We're going to concentrate on some differences that we see that makes the chemistry of rivers a little bit different. Those differences are centered on flow, downstream transport, and then the changing of geology. Basically, does the substrate of the stream, the sediment, um, the bedrock change as you go downstream? Now, when we think about a lake, there's always this vertical environment component, right? Where you have over here, this is a lake here, not a stream, right? Where you have this stratification where you can, at times, depending on the lake, right, you can have an anoxic hypolimnion. Now, the thing about streams is they have that helical flow, remember, right? So the forcing of the water moving and having that helix going around, right, makes the water never get stratified, right? Even the deepest rivers in the world, the Amazon River, 300 feet deep in places, um, there's still oxygen down there, right? You get oxygen taken from the top of the stream when it's in contact with the air, brought way down. In even the Amazon River, which can go straight for lots of time, like miles and miles, still has that helical flow. The thing is, where we do find anoxic water is possible in slack waters. Okay, um, so this area right in here, right? This is the Mississippi River, and we have this flow refuge where you can see, the water is no longer the turbid brown like it is out here. It's dark and clear, and then there's all this algae. You can see this big algae bloom in here. Um, this water is not moving, so it can stratify if it's deep enough, which I think this place I've been here it actually is. So um, in smaller streams, though, what we see is that smaller streams basically have less volume for compared to the surface area, right? There's a lot of surface area in a stream. So like a turbulent flowing river, gas gets in there very easily. Gas gets in and also gas gets out. Okay, so um, what we see is in the smaller streams, diffusion keeps oxygen at its saturation point, CO2 at its saturation point, right? So the streams are not, they're very rarely limited with oxygen, okay? And so what determines how much oxygen you have in a stream, a small stream, is pretty much the physical processes, that being temperature and then whether it's mixed up or not. Larger rivers are different though. There's much less surface area for the total volume, right? So photosynthesis and respiration are going to dominate the gas dynamics, not the physical processes, right? The water can be very, very cold, but if there's a ton of respiration going on and not that much photosynthesis, there's not really going to be that much oxygen in like a big river all through the the water column. Now they're at the edges of the stream. There might be some differences, right? But what we're talking about is, the most of the river channel here. Now, excuse me, pollution can have an effect. Adding nutrients to a stream is going to increase microbial respiration. So, in eutrophic rivers, you'll oftentimes have much more respiration going on. It can be oxygen limited. Um, what we see then, whether we're talking about a big river or a small river, I guess groundwater is going to be more important from small up to medium-sized rivers. But groundwater inflow is much more common in streams than it is in lakes. Lakes just don't have the water flow is kind of at equilibrium with each other, so you don't have a net transport of groundwater into that lakes. I mean, you could have like springs feeding into a lake, but that's less common. Groundwater always is coming into a river, kind of no matter how big it is. So and what we see is those streams that have a lot of groundwater influx are oftentimes low in oxygen and high in CO2 because that water has not been in contact with light, so there hasn't been photosynthesis going on. So especially in like areas that have rocky river valleys, there'll be a lot of groundwater influx that can really change the dynamics of the stream. So let's think about nitrogen. Okay, and the big thing about streams is denitrification. Okay, that's when you've already fixed nitrogen, and you made it to ammonia. It's been turned into nitrate or nitrite. Okay, the denitrification process then is this blue arrow, going from nitrate or nitrite to back to diatomic, atmospheric oxygen or atmospheric nitrogen gas, right? Now, the thing is, since what you're doing, the bacteria that are doing this are taking off the oxygens. And for them to do that, it needs an anoxic environment, right? Because nitrogen, when those oxygens basically get ripped off, nitrogen is very reactive with oxygen. So to do that, you need to not have oxygen in those in the water. So where do you see denitrification happening are in sediments, slack water areas, or in really low flow habitats. And what we've done is when you take a river and levee it, right, and put the levees here to protect the land over here from flooding, what you're doing is you're eliminating those low flow habitats. Let's go back to a picture, this one, right? So this is the Mississippi River where all in here, all these like really light green areas, these are those low flowing habitats where there's like all these slack water areas. They're all over the place here, right? Now, if you look at the Mississippi River, then basically from the middle of Iowa all the way down to Louisiana, what they've done to the river is, so the main channel is right here. What they've done to the river then is put levees right along the river, okay? And essentially they don't let the river flow into all of these habitat areas. So these are essentially gone now. Okay, so let's go back here. Since these levees are here, then you get rid of most of the sediments that are anoxic. You've gotten rid of pretty much all the slack waters and the low flow habitats, such that denitrification doesn't happen really anymore. And when you combine that with in the Mississippi River Valley, this is total nitrogen yields. Basically, this is how much nitrogen is being put on the land due to farming. And we see the darker it is, that's where we put more nitrogen for fertilizer. And all of that essentially, all of this nitrogen here flows into the Mississippi River, and that nitrogen doesn't have a chance to get denitrified. So then this is what is causing the dead zone in the Gulf of Mexico. Basically, the nutrients and everything is just shunted in a pipe all the way downstream to Louisiana. Now, as a stream is flowing, though, it's going to hit um, different geology, right? Just as a stream flows through the land changes. So the ions that you find in the water are from two places, from where the water just came from and the parent material of like what the bedrock is, what the water is flowing through the bedrock, right? So if you go from um, a river coming out of a granite area into a limestone area, as that water that's going through the granite is not going to have any that much carbon in it. But as soon as it flows into the limestone area, it's going to be picking up a ton of that carbon and really get that carbonate buffering system from those rocks. But this is also dependent on discharge, right? So if there's a bunch of rain going on, that there'll be like more faster flow than all of the ions can basically diffuse from the sediments, and it'll like dilute the water. And then there's also the factor of sediment supply, how much sediment is able to be moved down with the stream. But what we oftentimes see is that um, climate can also determine this. So with this discharge here, um, when you're going through a really arid or xeric area, so a dry area, um, there'll be a lot more evaporation that can then cause much like a concentration of the ions in the water. So in certain arid areas, what we find is that salinization is a big problem. So what happens when you put either a center pivot? This is a center pivot irrigation system, right, where this arm, swings around and waters this whole crop here, um, or just the flow irrigation that we see here on the bottom left. What happens is that water eventually gets evapotranspired, right? Plants are sucking up that water and then releasing it through their leaves. So what that happens then is think about all the water that's put on this field here. Then think about all the water that drains off that field. If you're if 3/4 of that water is taken up by those plants, that drained water, that water that's coming off, is going to have a whole lot more of the salts, about 4 times, right? If you take off 3/4 of that makes the water have 4 times the amount of salts. So oftentimes what we see is that water that comes out of an irrigation field can be brackish, can kind of be salty. It depends on the source and how much water or how much salt was in that water to begin with. But getting rid of that water can be problematic, and oftentimes it goes right back to the river. And in really arid areas, then where the river is already pretty highly concentrating, adding this extra irrigation, and it's not just irrigation for a couple fields, it's irrigation for the entire watershed, which can make the river itself become almost like a saltwater river, and that becomes a big problem. So what I wanted to let's shift gears here and think about the underlying substrate. Okay. um, Specifically in reference to acidity of water. Okay, so we have a continuous acid input. Okay, this is basically the hydrogen ion concentration, essentially the pH of rainwater. Okay, and what you can see is rainwater is always just a little acidic, but it naturally shouldn't be. So here it's 5.5. I'm trying to think. It gets into the high fours here, and then over here it's in the low fours. Okay, now this is due to like sulfuric acid being released and nitric acid being released by coal burning power plants. So we see, the general wind patterns are the prevailing westerlies that blow that way. So we get all of America's coal and sulfuric acid basically dropping out on the Northeast. This is also area where we have the softest water. This is all of this area is granite, and it doesn't have much limestone, so there's not that much carbonate in the water. So there's very little buffering that can happen due to the water. So if you have this continuous input, um, oh, here is the basically hardness of the water. And what we see is, these are the limestone areas where we have a lot of limestone and the water is really hard, meaning has a lot of carbonate. And then the purple areas are the areas where there's a lot of granite and essentially the water is very soft. It doesn't have a lot of carbon in it, so it can't buffer that much. So when you combine those two things together, what we see is rivers that are flowing through the Northeast and getting this high acid input um, are starting to reach the point where the organisms are having trouble. At least the organisms that have a calcium carbonate shell are having trouble surviving in there, and they can have really thin shells due to this acid rain because essentially the water is dissolving away their shells. and that obviously becomes a big problem. All right, with that, see you later.